All right, it is day 3 of this operating system project I'm trying. Um, just want to say a few things first before I start. I've gotten a ton more feedback than I was anticipating. 47 comments, right? And so yesterday morning I had 15 or so subscribers, and now there's 106. So I was not expecting so many people to find this and be interested. But it's been really fantastic because I've gotten a lot of really helpful feedback and some not so helpful feedback, but lots of feedback. I want to be sure to thank this guy, um, Xyloflake, something with an X. And he suggested I make a Discord server. So I made a Discord server. And right now it's just the two of us on here, but it's been extremely helpful. He's helped me a whole lot, giving me a lot of resources, shown me a lot of things I've been doing wrong, a lot of encouragement. It's just been super helpful. If you want to get on here, there's like Teach Kai, where you can tell me things I should know. There's feature ideas. I'll post the videos I make here, general for whatever, and that's about it. Let me go back to Arc. If you want to get on, all the video descriptions will have a link to the server right here. And what else did I have to talk about before I got started? Okay, so a lot of the feedback was basically saying that I have no idea what I'm doing and I'm overly optimistic, which is fantastic and entirely true. There's also a lot about how I shouldn't have been using LLMs and whatnot. So, about all that, I'm gonna, in this video, take some steps back in response to what wiser heads have been telling me and try to start actually learning and try to actually understand what I'm doing at a slightly or hopefully much deeper level. And yeah, just see how that goes. I'm gonna try. Here's my goal, right? Here's my goal. My goal is to not write or minimize any code that I have to write that I don't fundamentally understand, right? And I know there's probably gonna have to be some stuff that I don't really understand that's like directly related to like literally how the hardware of computers works, and that's fine because I don't need to build my own computer to make an operating system. But I don't want to write code I don't understand. And I know in the first video I was definitely doing that. My hope was just to kind of bootstrap it and get it to a point where I could just start writing. And so I kind of made an exception there, but some people weren't so happy about that. So I'm going to try not to do that going forward. And yeah, so I got some recommendations over here. I'm going to move this to my other monitor on where to start reading, to start learning this stuff. Let me find where that was. Where is it? Can I search? Oh, check it out. Oh, here we go. Okay, so here's what I'm going to start with. These are what Xyloflake suggested to me. I'm going to start with, well, here's what I'm going to start with. I'm going to start, so I got some resources here that I got from him. All of these are from him. There's I knew about this. There's the OSDev Wiki. I think this is like a fork of it. It's a little bit confusing because the other one doesn't have this thing. I figured I'd read through introduction, required knowledge, and beginner mistakes. And then jump over to this, which is understanding how CPUs work at kind of a high level, I think, which will help before I get into like ASM and stuff. So let's just start. I'm going to sound like the Primogen, just reading articles to you guys. Make sure that I'm doing all right over here. Okay, let me blow this up a little bit. All right. Welcome to operating system development, the great frontier. Not all make it in this field. That's encouraging. How many don't even pass the hello world of OS development? Sorry, many don't even pass the hello world of OS development, but perhaps you will go further and create the next Linux or Windows. Or your goals lower, Minuet OS, or even CP-M. I don't know what either of those last two are. Whatever your goals, OS deving is the great pinnacle of programming. Oh, perfect. That's what I'm looking for, is the pinnacle. But you're not alone. In fact, this entire website, including the forums and this wiki, are dedicated to OS deving. And not only about this is not only about great programming skills, but it is about community and developing friendships, be those friendships between fellow forum members or IRQs and processes. What do you need to succeed in OS deving? You should read the Getting Started article. That's next, I think. Or no, that's fourth. I'm not doing that today. I forget. If you're going to use C or C++ as your language of choice, you're required to build a GCC cross-compiler first. Okay. I think I'm going to use Rust still. If you prefer to use other languages, then it is important to have some tools, or if there's no such tools, it is often only your efforts that can help you. But going along with your preferred language can add some motivation and excitement during your work. Yeah, I like Rust. I mean, it's got some flaws, but it's pretty good, and I was thinking I'd just keep using that. I'm going to make this narrower. It's a little hard to read. What is an operating system? Oh, perfect. An operating system is a software controlling the operation of a computer system and its resources. Among other things, there's one very important criteria common on all operating systems: capable of loading and executing user programs, providing standardized, hardware-independent input-output interface for them. Okay. Major functions of operating systems may include managing memory and other system resources, imposing security and access policies, scheduling and multiplexing processes and threads. That sounds thrilling. Launching and closing other programs dynamically, providing a basic user interface and application programmer interface. See, this to me sounds like a ton of fun to make. Not all operating systems provide all of these functions. Single tasking systems like MS-DOS would not schedule processes, while embedded systems like ECOS may have a user interface or may work with a static set of user programs. An operating system is not the computer hardware, a specific application such as a word processor, web browser, or a game, a suite of utilities like the GNU tools, which are used in many Unix-derived systems, a development environment, though some OSs such as UCSD Pascal or Smalltalk 80 incorporate an interpreter and IDE. Okay. I'd like to have an IDE. That'd be cool. A graphical user interface although many modern operating systems incorporate a GUI as part of the OS. Yes, long term, I would like for my OS to have a GUI. That sounds fun. It sounds nice. While most operating systems are distributed with such tools, they are not themselves a necessary part of the OS. Some operating systems, such as Linux, may come in several different package forms called distros, which may have different suites of applications and utilities and may organize some aspects of the system differently. Nonetheless, they're all versions of the same basic OS and should not be considered to be separate types of operating systems. The kernel of an operating system is something you will never see. It basically enables any other programs to execute. It handles events generated by hardware called interrupts and software called syscalls, and manages access to resources. The hardware event handlers, interrupt handlers, will for instance get the number of the key you just pressed and convert it to the corresponding character stored in a buffer so some program can retrieve it. Yeah, that makes sense. System calls are initiated by user-level programs for opening files and starting other programs, etc. Each system call handler will have to check whether the arguments passed are valid, then perform the internal operation to complete the request. Okay, most programs do not directly issue system calls, except for ASM programs, for instance, but instead use a standard library which does the ugly job of formatting arguments as required by the kernel and generating the system call. For example, the C function fopen eventually calls a kernel function that actually opens the file. The kernel usually defines a few abstractions like files, processes, sockets, directories, etc., which correspond to an internal state it remembers about last operations, so that a program may issue a session of operation more efficiently. What is a shell? A shell is a special program that is usually integrated in an OS distribution, and which offers humans an interface with the computer. The way it appears to users may vary from system to system, command line, file explorer, etc., but the concept is always the same. Allows the user to select a program to be started and optionally gives it session-specific arguments. Allow trivial operation on the local storage, like listing the content of directories, moving and copying files across the system. Okay. In order to complete those actions, the shell may have to issue numerous syscalls like open file X, open file Y, and create it if it doesn't exist, read content from X, write into Y, close both files, write done to standard output. Perfect. The shell may also be used by programs that want to start other programs, but do not want to do this themselves. Like completing file patterns like MP3, retrieving the exact path of the program, etc. Okay. Modern shells can also have various extra features, such as the following: auto-completion. By pressing the tab or any preferred key, the word the user is typing will be completed to a valid shell command, a file, directory, or something else. Pressing the auto-complete key multiple times cycles through other completion possibilities. Okay. Yeah, character insertion. Yep, shell history. Yep, scrolling, scripting. We know about these things. Okay. What is a GUI about? The graphical user interface GUI is the most visible part of any operating system that has one. Its role goes beyond a simple drawing library. It also must be able to catch user input events and dispatch them to the proper object. Update the internal information of what is to be displayed where on the screen, determining which parts of the screen need to be redrawn. Update the visible screen contents, redrawing the necessary parts. Do so in a way that feels natural, intuitive, and responsive. Desktop environment, window manager, widget library. When you're launching into a KDE or Windows session, that is a desktop environment, i.e. a graphical shell providing the functional environment for all lower level functions. The part of the system responsible for organizing the windows of the various running programs, their resizing, closing gadgets, window borders, scroll bars, etc. is the window manager. Finally, you have the subsystem that does the drawing of control elements, rendering documents on the screen, etc. This is commonly called the widget library. However, there are alternatives to widget libraries, usually in the form of declarative languages. What? Example, Mozilla's XUL, Qt's QML. Mozilla. What was it? XUL? Mozilla. XUL. XML user interface language. It's a user interface markup language developed by Mozilla. It's an XML dialect for writing graphical user interfaces. What does it look like? Oh, okay. That is interesting. Very interesting. GUI related form threads. Will you implement a GUI? Yes. GUI design? Yes. Handling input events in GUI? Yes. I'm sure I'll get to those later down the road, but that's pretty far off, I think. There are various reasons why people choose to develop an operating system. Each individual developer may have their own, but some reasons are common among some, if not most developers. Having complete control over the machine. Yes. Complete control. When developing an application or other user-based program, the developer has to take the code written by others into consideration. The operating system, the libraries, other programs, etc. It is a powerful feeling for the only code to be running on a machine to be your own. Yes, that does sound like an empowering feeling. Research. Quite a few operating systems projects are started as homework or research projects. While starting an operating system as a homework assignment in a pre-tertiary or first-year environment is generally considered a bad idea. Due to short deadlines. A long-term project is quite fine. Research projects are usually undertaken to improve on existing operating systems. A common beginner mistake, however, is to underestimate the time needed to write an operating system from scratch. Check that box. To replace the current available operating systems, maybe they don't have a particular feature that the developer wants. Maybe they just generally suck. Linux is bloated, Windows is unstable, etc. This may be for profit, although any returns are likely to be a long time away. Because it's fun. This is my reason. Low-level programming is a fun and exciting task because you have to do everything. This may seem more difficult. It is, don't worry. Perfect. But by the same reasons, more fun. You know how everything works, how it all fits, and the innermost workings of your program. Unfortunately, many operating systems are undertaken for the wrong reasons. See beginner mistakes for a list. I think that is our next reading material. No, first required knowledge. Okay. Beginners in OSDev are strongly recommended not to skip this. I'm not skipping it. I'm reading it. Writing an OS is not a beginner's task. In fact, writing an OS is usually considered the most difficult programming task. Okay, that's a little bit intimidating. Above average programming skills are needed before even considering a project like this. Failure to comply will make you look silly. I'm not too afraid of looking silly. So, I don't know that I necessarily have above average programming skills. But yeah, I don't know. We'll just keep going. Developing an OS requires these knowledge. These knowledge, is that correct English? Developing an OS requires these knowledge. I don't know. Basic computer science, basic computer science and then intimate familiar. Oh, okay, with hexadecimal and binary notation, as well as Boolean logic and similar fundamental knowledge like data structures, their construction and manipulation, searching and sorting algorithms, abstract programming concepts, etc., etc. That's pretty. I think I got that. Language and vocabulary, ability to read and write technical English at a competent level. You guys hear me? You can judge. Virtually all technical documentation is in English, yada, yada, yada. Language and vocabulary, part 2. Most operating systems featured on this site, as well as most of the code snippets and examples, are written in C or C++. Individuals should be competent in making heads and tails of it, even if they choose to use another language, since C is the lingua franca of programming. Okay, I learned C a while ago. So, I mean, I think I'm comfortable reading it. I wouldn't count on myself to be able to write it well. Assembly, knowledge about the low-level language assembly. Yes, this is my next task. Read a book, take a course at school, write some user space code, and familiarize yourself with it. You will need it even if you plan to write most of your operating system in a higher level language. Yep. Programming experience. Learn about programming with an OS project. Learning about programming with an OS project is considered a bad idea. Not only should you know the language in which you'll be developing inside out, you should also be familiar with version control, debugging, etc. In short, you should have written quite a few user space programs in that large language successfully before trying OS development. So if I use Rust, I've definitely built some projects with Rust. I mean, nothing like huge or particularly sophisticated, but I'm fairly comfortable in it. I'm definitely not a master at it, but maybe I'll become a master at it by doing this. I'm definitely a lot better at Rust than I am at C, I'll say that. Programming practices. You should know how to write both code and user documentation, and be prepared to carefully document all aspects of your code and design, even if the project is purely for your personal use. Also, you should learn and use suitable code management practices, including setting up and using an offsite repository. Savannah, GitHub, Heroku. These 2 practices alone not may, but will save you a great deal of trouble in the future if you follow them. I'll use GitHub. It's cool. Unix experience. You will soon notice that many of the tools used in OS development are developed for Unix and later ported over to Windows. The Linux kernel is often used as a reference for examples for how things can be done, and many of the hobby operating systems have some resemblance to Unix. Having experience with Unix command line, preferably Bash or what's KSH? It's like ZSH. Zish is a very important requirement. Cygwin provides an easy to install Unix command line for Windows. Okay. If you haven't, go ahead and use Linux or a BSD for a while. For Windows users, this can be accomplished quite easily by using a virtualizer, see below, to host to host a virtual system without the need to repartition your home system. You could also install WSL within Windows itself to get access to the Unix command line for Mac OS. You can simply use the terminal. Mac OS is built on Unix variant kernel, a combination of the Mach and BSD kernels. So as long as you have Xcode and an emulator or virtualizer installed, no further tools are necessary. Although you'll need to set up a cross-compiler. Okay, I'm using Zish. Oh my Zish, to be particular. Toolchain. You must know the behavioral details of your compiler, assembler, linker, and make utility. You should know what the emitted warnings and errors mean. You should have documentation of the tools you use at hand and refer to them before asking the community. Rest assured that any possible beginner's questions about GCC, GNU as, NASM, GNU ID, or is it LD? That's the linker, isn't it? Visual Studio and Grub have been answered twice over. Search before you ask. Emulators and virtualizers. Familiarity with tools such as Box, a VirtualBox, QEMU, or Virtual PC is key to reasonable turnaround in development. I mean, I've used QEMU. I've actually used this one too, VirtualBox. And I can't say I have deep familiarity with them, but I mean, I'll probably figure it out as I go, no? These tools provide a buffer between your real hardware and your test system. And while these can be learned for the specific purposes of OSDev, you will certainly want to be aware of what they are and where to get them before beginning an OS project. Executable formats. Kernel space development has many additional requirements unknown to application development. Being able to parse executable binaries is one of them. You do want your OS to load and execute applications, don't you? Make yourself familiar with executable file types and their internal structure and how a linker generates them. That is not something I'm particularly familiar with, I will say. The platform. He should have studied the manuals for the processor you will be programming for. They contain the information you need to design your kernel in the first place. Asking for information that can easily be obtained from these documents will only give cause to read the friendly manual responses or simply RTFM. The concept. You should have an understanding of how existent operating systems function at the technical level. Example, by having read some books, what is good or bad about them, and how you want to go about your own OS. Having finished this tutorial and then asking what now in one of the forums will just make you look silly. Okay. A particularly good and excellent, but unfortunately unfinished as of yet, book on the topic. Operating systems from 0 to 1. This focuses on everything you need to know, from the transistor to logic circuits, assembly and C language, ELF, format, and debugging, etc. Read and understand this book to get a quick start on required knowledge. OS 0 to 1. Look, it's got 12,000 stars. Oh, this thing's old. How does one read the book? Here? Whoa, this thing is long. Just 84,000 lines. Okay. Perfect. Can we go back to here? I think my next step then is beginner mistakes. These, I have been told, I've made already, so should be fun. The idea to write your own OS brought you here. It did. This wiki is about giving you help, pointers, and references in your undertaking. However, it is quite common that newcomers make certain mistakes or have common misconceptions about what is involved in the topic. That is not bad. Thank you. Many others made these beginner mistakes before, and many will do so in the future. This page is about making sure you know what you're about before digging into the provided information. What this is not. This may look like a set of tutorials to copy and paste plus a forum to ask questions whenever you get stuck. This is not so. We fully expect you to carry your own weight and be an experienced programmer of user-space applications before you set out to write your own OS. We also expect you to have read about OS design and that you have studied relevant documentation of your platform of choice. Do not expect this wiki or the forum to be some kind of complete guide. Be some kind of complete guide to my own OS, let alone a guide to programming skills in general. Okay. What you find here is documentation left behind by those who came before you, who found out about these things by reading technical documentation, available source code, and forum postings, as well as by trial and error programming. Some of it was written to those people, so those people could look it up again later. Some of it so that we could point to a wiki article instead of explaining a subject all over again. What you find here are little hints and road signs that might help you on your path. It is not a complete map to Oz, nor should it be. If you don't already have a good idea of what a stack is or how to use a debugger, we won't go out of our way to explain it to you. Okay, visit these 2 pages. You will see they mostly deal with OS specifics, not a general introduction to the topic. This is not a flaw, that's by design. If you are looking for general programming enlightenment, You should rather visit general programming sites like Stack Overflow and become a developer first before you aspire to become an OS developer. I am a developer, I like to think. This wiki will not be expanded into a beginner's handbook because that's not its purpose. It is for answering the advanced questions that arise when people feel they're ready for the plunge into kernel space programming. A hard truth. I'm ready. Programming novices should probably not be considering OSDev yet. Experience in low-level coding in assembly language and or systems language such as C is pretty much the minimum necessary and to even understand the topic well enough to work in it. What's more, this is growing ever more true by the year as the number of different standards, computer and mobile devices, peripherals, and design concepts continue to expand. It was one thing for someone like Dennis Ritchie, Richard Greenblatt, Kerry Kildall, or Steve Wozniak to write a simple OS for hardware, which was relatively straightforward in comparison to current machines, which they already knew intimately, and which had no standard specification to adhere to or even cruft to maintain backwards compatibility with. This is no longer true on current generation stock hardware. Furthermore, each of them was already a seasoned engineer who had already done years of systems programming. By then, they only provided the foundations for the systems. The bulk of the work was done by small armies of subordinate developers after the nucleus of the system, the kernel in modern jargon, was in place. There are exceptions to this rule, but not many. Don't expect yourself to be 1 in 1,000. If you think you are, read up on the Dunning-Kruger effect and consider the matter again. The Dunning-Kruger effect is a cognitive bias in which people with limited competence in a particular domain overestimate their abilities. That's relatable. Oh, and for the record, Linus wasn't quite one of them. He was a graduate student when he wrote the Linux kernel and had been coding in C for years. While he was well short of that 10-year mark, as a grad student who had turned his hobby into his master's thesis, he had more time on his hand. Okay, this is like history stuff. Can I skip over some of this? Okay, they're basically saying it's really hard. Now, you shouldn't get too discouraged by this. The point is not that you can't do this, but that if you were like most of us when we started out, you probably can't do it yet. That sounds right. Patience can be a virtue when starting out on a project this large. Can be. I feel like it always is a virtue. Is there a tutorial on ... Because this place cannot and does not cater to beginner developers, the question of which other place provides a tutorial, good explanations, or easy to understand reading is often asked. However, they do not exist. Difficult subjects cannot be described with light prose, just like how there are enough things that are too complicated for a monkey to properly learn. Okay. If you have trouble reading official documentation, this would be a good time to practice. In fact, the vast majority of tutorials currently out there are known to be broken in at least one way, so you're generally better off not trusting them in the first place. Scope, deadlines. University, hobby, or commercial, this is a hobby. Operating system takes time. Linux kernel took over 1 year, very little to get the semblance of usefulness, and all he did was mimic existing and well-documented behavior to get it already existing user space. Moreover, every project as successful as Linux, where there are literally hundreds of projects that consume a man-year or more. Okay, so it's going to take a long time. Therefore, plan a reasonable roadmap of what you want to get done. Okay, do not assume that in 3 months your OS will have a GUI and voice recognition, because operating system development does not contain any rad tools in it at all. In fact, it is completely void of them. Void. That's a joke. Get it? Haha. End goal definition. When starting out a project, you should estimate your end goals, your end users, the purpose for which the project is developed, etc. Operating system development is no different to this. Having a rough idea about your goals will give you motivation and the direction where you need to head. However, don't get stuck at your initial end goals when something better comes to your mind. Unfortunately, many OS developers don't estimate what their final OS will look like. Therefore, they don't know in which direction to head and resort to asking what's next. It should be mentioned, however, that to estimate your end goals, you should be aware of the whole technical concept of how existing operating systems work. Okay, I'm not really. Don't get it in your mind. This will make you rich. That's fine. I'm not. It's not gonna make me rich. I know that. assuming it will go nowhere. In contrast to the above, some people assume their OS will go nowhere. For this reason, their projects have ugly code, don't take important aspects into account, and in general rely on ugly hacks. Worst of all, they make decisions that don't result in usability and extensibility. This is where their assumption becomes a self-fulfilling prophecy. Okay. In reality, while the chances of getting your OS running outside of your test machines are low, there are enough advanced OS projects that have started from this very community. That's like the most encouraging thing in this whole discouraging document. Avoid ignorance. Beginners often ask, what is the easiest way to do X, rather than what is the best, proper, correct way to do X. This is dangerous, as the newcomer doesn't invest time into understanding the superior way to implement something, but instead picks a conceptually simpler method copied from a tutorial. Instead, the simpler route is often too simple and ends up causing more problems in the long run, because the beginner is ignorant of the superior alternative and doesn't know when it is better to switch. What is so bad about taking the hard route instead? Common examples include being too lazy to use a cross compiler, not understanding real mode, unreal mode, protected mode, and long mode, or jumping far too fast from one to the other without first understanding how to gather all of the vital configuration and use all of its capabilities fully, especially detecting base capabilities with BIOS during boot and initialization. Relying on BIOS calls that are not standard, not learning to write hardware drivers in your own OS and under Windows and Linux for greater convenience. Exposing test capabilities globally using flat binaries instead of ELF, not learning about executable, archived graphics, document, and other file formats, and compression algorithms, and so on. Experienced developers use the superior alternatives for a reason, which you might not understand yet. Experienced developers choose to use the inferior methods in some cases, but that's because they can carefully analyze when it is appropriate, and they know when not to use it. As a beginner or intermediate developer, you will likely not know these methods and technologies well enough to reason whether the inferior solution is good enough for you. Remember that if you oppose a method, you should know it well enough to know everything that is wrong and right with it. That's good. Either way, laziness and ignorance only leads to trouble down the road. When in doubt, pick what appears to be the conservative choice rather than the simpler. Design, GUI design, it will likely take you several years starting from scratch to get to the point where you can actually do anything GUI related. Okay, well, I'm not quite 20 yet, so we got time. The looks of a GUI are secondary at best, as they can easily be changed retroactively, which really decides the usability of a GUI. Man, I can't read today. What really decides the usability of a GUI is the functionality, and that isn't expressed in mock-up graphics. If your aim is to create a better looking instead of a better OS, consider implementing a window manager. Popularity, my OS will be more popular than Windows, Mac OS, and Linux. Of course it will. This is extremely unlikely. To achieve this requires a lot of time, money, and knowledge. Not everyone will download your operating system because they may not know what an operating system is or how to install one. Your operating system has security risks. Your operating system supports web applications. Your operating system is not fully functional, minimal command line interface, or bad GUI. Sure. You'll be lucky to get a few people to use yours. I'm not anticipating anybody using mine, not even myself. Unless, for fun, I'll use it, but there's no way it's going to replace like Mac OS for me. The only reason why the popular operating systems of today are popular is because they were available and addressed needs decades ago when there were fewer alternatives. Memory usage. I want to use less than a couple kilobytes. Sorry, that's probably impossible. On OS, using such little memory will be almost unusable. Forget about file system drivers, disk drivers, USB drives, etc. For developing something small, just make a simple bootloader, not an OS. Another option would be to try native Forth. See this? I skimmed through this before. This entire paragraph is about Forth. I don't understand what Forth is. But it's not what I want to do. I got that much. Okay, OS emulation. My OS will be able to run programs from Windows, Mac OS, Linux, and even PDP-11 programs. Sorry to burst your bubble, but it probably won't. Emulating even just a single system takes years of work, especially when it's proprietary, such as Windows or Mac OS. Linux is probably the easiest out of the four. Wine let's check out why. Is this, despite being in development since 1993 and being written in user space, has still got problems with many programs. Running Windows applications on other operating systems is what it is. Okay. Huh. That's interesting. So instead of focusing on emulating other systems, focus on your own. Design it, develop it, and be friends with it. Cool. Programming languages. Some languages are well suited to write a kernel, others are less so. Read the page about using other languages other than C. Alright, well I know Rust is fine. I think. I hope. And I'm pretty sure I want to use that, so. Kernel image. Booting problems, especially in early stages and with a self-built bootloader, which is what we're going to do. Last video I pulled in the bootloader crate and then realized that that would not mean that I was building it from scratch, as the title suggested. So we're going to write our own bootloader. The reason for booting problems is frequently that too few sectors are fetched from disk. Either adjust the amount of sectors you fetch from the disk or have the bootloader second stage loader parse the file system. Not sure what that means yet. Troubleshooting. Ask for help. Before asking for help in the forums or IRC, you should be taking all the possible steps to diagnose the nature of the problem yourself. In the case of problems like triple faults or random exceptions, it's a common mistake to make assumptions about the cause of a problem. Make use of a debugger or print statements to locate the exact point when an exception occurs. Using an emulator and a debugger, such as GDB and BoxQemu, will help you locate problems which are difficult to trace. If you provide some theory about your problem and actions you have already taken to solve it, people will be able to help you much easier, even if your theory is not correct. It at least gives people an idea of your views on the problem and the strategies you might have already tried, as well as what you might have missed. In general, put as much work as possible into solving the problem yourself before asking others for help. Before you post, ask yourself, have I done everything I can to diagnose and solve this problem? Often you'll learn a lot in the process, and you'll likely be able to solve the problem and similar problems in the future yourself, without the help of others, which is a good thing. When you ask for help, provide the code relevant to your problem. However, the problem may be located somewhere else, so give others a way to look at the other parts of your code as well. If you're using something like GitHub or Bitbucket, this is slightly easier, but there are certainly many other ways. In regards to the forum, read the forum rules. They are required reading and will improve the quality. Okay. Let people have lives too. Fun fact. If you need leave to do something and want to check if you missed anything, there are logs available to go. Yeah, okay. This is just about the forums. Naming is usually the last problem we solve. I already solved it, so I think I'm gonna call it Humble OS. Because I think it's a good thing to be, and it'll be a nice reminder just to have that right there all the time. Naming is usually the last problem to be solved, even while we all wish for a cool name for our cool concept. Since the coolness of a name is a matter of taste, we cannot help you in finding it. Okay, I'm Humble OS. It's a Humble OS is what it is. Project website. Many newcomers to OSDev create project websites before they have anything worth showing on the website. There's no value in creating a website, making dramatic claims about the future plans for your project before you've got any idea where your project is heading, or any code, screenshots, or downloads to showcase what you've already produced. Such a website looks dead and creates a bad reputation. Announcing your website, such as in the announcements forum, whatever, or linking to it, when there's nothing more than a welcome to insert fancy project name here message on it, makes people lose interest in your project before you've even started. And if when you do eventually produce something worth showing off, you'll be faced with an already terrible reputation that will be hard to overcome. That's good advice. Okay, no website. The number one beginner mistake as seen in the announcements forum. It usually comes in one of two forms, although the forums have quite a bit of overlap. Community projects. Don't overestimate your chances of getting people interested in your project. Even the more successful projects usually consist of one, perhaps two people actually working on the code. Okay, that's fine. Brooks' law states that the more people there are on a project, the longer the project takes. Yep. The only way around this is to split the project into parts, which you get people working on and only on. Good luck. Recruiting. There are some things you need. Okay, I'm not trying to recruit anybody really, so. Sweet. So that was introduction, required knowledge, and beginner mistakes. Getting started will be next. Before we do that, we're going to back up, as suggested to me, and read this. Start reading this. I don't think I'll finish. I definitely won't finish this today, but it's not super long. Like, this is the introduction, and then there's the basics, just like that much, and then multitasking, it's even shorter. Exec, a little longer, and then there's the page about elves, which I'm looking forward to. Check it out. It's elves, which is not super long either. These are all kind of short. Yeah, that's reasonable. A little longer, and that one's in. Look, the end. Cool. This looks really cool. So I'll maybe read today like intro and basics, and then call it a day, and continue tomorrow. From the beginning, I've done a lot of things with computers. Who is this? Is it Lexi or wait, Lexi and Hat Club? So this is Lexi. This is Lexi. Wow, looks like she has done a lot of things with computers. What's Hat Club? Hat Club. Oh, look, this is the book. Whoa. These people look cool. A home for high school hackers. Huh, that's really neat. Okay. I've done a lot of things with computers, but I've always had a gap in my knowledge. What exactly happens when you run a program on your computer? I thought about this gap. I had most of the requisite knowledge, low-level knowledge, but I was struggling to piece everything together. Are programs really executing directly on the CPU, or is something else going on? I've used syscalls, but how do they work? What are they really? How do multiple programs run at the same time? You look at the CPU, you have a question, you have an idea, and you go research it. Okay, that's kind of what I'm doing. I cracked and started figuring as much as possible. Started figuring as much as possible. There aren't many comprehensive systems resources if you aren't going to college, so I had to sift through tons of different sources of varying quality and sometimes conflicting information. A couple weeks of research and almost 40 pages of notes later, I think I have a much better idea of how computers work from startup to program execution. I would have killed for one solid article explaining what I learned, so I'm writing the article I wished I had. Whoa, this is so cool. And you know what they say, you only truly understand something if you can explain it to someone else. Okay, the basics. Let's read through this. All right. The one thing that surprised me over and over again while writing this article was how simple computers are. It's still hard for me not to psych myself out, expecting more complexity or abstraction than actually exists. But there's one thing you should burn into your brain before continuing. It's that everything that seems simple is actually that simple. The simplicity is very beautiful and sometimes very, very cursed. Let's start with the basics of how your computer works at its very core. How computers are architected. The central processing unit, CPU, of a computer is in charge of all computation. It's the big cheese. The Shazam alakablam. It starts chugging as soon as you start your computer, executing instructions after instruction after instruction. Sorry. The first mass-produced here. Let me make this bigger for you guys. Oops. Is this better? Okay. The first here, I can even move this guy over to this side. Is that better? All right. The first mass-produced CPU was the Intel 4004, designed in the late 60s by an Italian physicist and engineer named Federico Faggi. I don't know how to say that in Italian. It was a 4-bit architecture instead of the 64-bit systems we used to get. Wow. And it was far less complex than the modern processors, but a lot of its simplicity does still remain. The instructions that CPUs execute are just binary data, a byte or two to represent what instructions is being run. The opcode, followed by whatever data is needed to run the instructions. What we call machine code is nothing but a series of these binary instructions in a row. Assembly is a helpful syntax for reading and writing machine code that's easier for humans to read and write than raw bits. It is always compiled to the binary that your CPU knows how to read. So this is the machine code. This is it in hex, and this is it in assembly. So this is the opcode, and then this is the data it needs, right? It says it, the opcode followed by whatever data is needed. So this is the needed data. Okay. An aside, instructions aren't always represented one-to-one in machine code as in the above example. For example, add EAX 512 translates to 0500020000. The first byte 05 is an opcode specifically representing adding the EAX register to a 32-bit number. The remaining bytes are 512, 0x200, and little endian byte order. Little endian byte order. Endianness. Gulliver's Travels. Whoa. Alright, that looks like something I'll probably have to get into, but save it for future reading. Diffuse Security created a helpful tool for playing around with the translation between assembly and machine code. Oh, that's cool. RAM is your computer's main memory bank, a large multi-purpose space which stores all the data used by programs running on your computer. That includes the program code itself as well as the code at the core of your operating system. The CPU always reads machine code directly from RAM, and code can't be run if it isn't loaded into RAM. The CPU stores an instruction pointer, which points to the location in RAM where it's going to fetch the next instruction. After executing each instruction, the CPU moves the pointer and repeats. This is the fetch execute cycle. You fetch, read instruction from memory at the current instruction pointer, execute, run the instruction, and then move the instruction pointer. Read instruction from blah blah. Fetch, execute, fetch. Okay. All right. After executing an instruction, the pointer moves forward to immediately after the instruction in RAM so that it now points to the next instruction. That's why code runs. The instruction pointer just keeps chugging forward, executing machine code in the order in which that has been stored in memory. Some instructions can tell the instruction pointer to jump ahead, jump somewhere else instead, or jump different places depending on a certain condition. This makes reusable code and conditional logic possible. This instruction pointer is stored in a register. Registers are small storage buckets that are extremely fast for the CPU to read and write to. Okay, each CPU architecture has a fixed set of registers used for everything from storing temporary values during computations to configuring the processor. Some registers are directly accessible from machine code, like EBX in the early diagram. Other registers are only used internally by the CPU, but can often be updated or read using specialized instructions. One example is the instruction pointer, which can't be read directly but can be updated with, for example, a jump instruction. Processors are naive. Let's go back to the original question. What happens when you run an executable program on your computer? First, a bunch of magic happens to get ready to run it. We'll work through all this later. But at the end of the process, there's machine code in a file somewhere. The operating system loads this into RAM and instructs the CPU to jump the instruction pointer to that position in RAM. The CPU continues running its fetch execute cycle as usual, so the program begins executing. Wait, let me mark, oops. Whoops. Mark this spot. And then, all right, I'm gonna read until here, and then that's like the halfway point. And I'm gonna call it a day. I'll do the rest next video. This was one of those psyching myself out moments for me. Seriously, this is how the program you're using to read this article is running. Your CPU is fetching your browser's instructions from the RAM in sequence and directly executing them. And they're rendering this article. Instruction pointer. Doink, 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 doink. Just bumps down, I guess, the line. Turns out CPUs have a super basic worldview. They only see the current instruction pointer and a bit of internal state. Processes are entirely operating system abstractions, not something CPUs natively understand or keep track of. That's really interesting. Wave's hand. Processes are abstractions made up by OSDev's big byte to sell more computers. What? I don't quite get that. For me, this raises more questions than it answers. If the CPU doesn't know about multiprocessing and just executes instructions sequentially, why doesn't it get stuck inside whatever program it's running? How can multiple programs run at once? That's a good question. If programs run directly on the CPU and the CPU can directly access RAM, why can't code access memory from other processes, or God forbid, the kernel? Speaking of which, what is the mechanism that prevents every process from running any instruction and doing anything? Speaking of which, what's the mechanism that prevents every process from running any instruction and doing anything to your computer? And what's a syscall? The question about memory deserves its own section and is covered in Chapter 5. The TLDR is that most memory accesses actually go through a layer of misdirection that remaps the entire address space. For now, we're going to pretend that programs can access all RAM directly and the computers can only run one process at once. We'll explain away both of these assumptions in time. It's time to leap through our first rabbit hole into a land filled with syscalls and security rings. Oh, sounds fantastic. Aside, what is a kernel, by the way? Your computer's operating system, like Mac OS, Windows, or Linux, is the collection of software that runs on your computer to make all the basic stuff work. Basic stuff is a really general term, and so is operating system. Depending on who you ask, you can include such things as the apps, font, icons, which go with the computer by default. Okay. The kernel, however, is the core of the operating system. When you boot up your kernel, the instruction pointer starts at a program somewhere. That program is the kernel. The kernel has near full access to your computer's memory, peripherals, and other resources, and is in charge of running software installed on your computer, known as userland programs. We'll learn about how the kernel has this access and how userland programs don't over the course of this article, okay? Linux is just a kernel and needs plenty of userland software like shells and display servers to be usable. The kernel on Mac OS is called XNU. I had no idea. And is Unix-like, and the modern Windows kernel is called the NT kernel. XNU. X is not Unix? What? Oh, GNU? XNU. I had no idea. That's so funny. Actually, that sounds like vaguely familiar. Like the whole not Unix thing sounds familiar. Huh. Where was I? All right, I'm going to stop there. This is my bookmark. 2 rings to rule them all is next. But I'm starting to lose my voice, and I got to get to work. So, what else? There's one other thing I was going to say before I finish. Oh, yeah. So I'm leaving, what is it, Friday? It's Friday. I'm making this video on Friday, March 28th. I'm going to be gone all of next week and into the following week. So I won't be doing another video till not next week, but the following week on Wednesday or Thursday. So, little break here. Yeah, thanks for watching.